In the last video, we stated some facts about the normal distribution, and specifically that its shape and position depend upon two parameters, the mean and the standard deviation. And we can see that we need both of those because that will affect our probability density function. Mu will cause the curve to shift left or right. Sigma will cause sort of a scaling factor. The bigger the sigma, the more spread out that 100% is, but the flatter the peak. Whereas for a really small sigma, we get really tight curves that are really high, and the full area accumulates between two values that tend to be closer together. So we can see that here. As I make sigma bigger, I have to go out further to accumulate all of that area under the curve. And as sigma becomes smaller, it can't be negative, but as it becomes smaller, you can see that most of the area is located definitely between 4 and 6. And as I change mu, I'm just going to shift that entire curve right or left. This is a perfectly symmetric distribution, meaning that if you were to draw a line at x equals mu, in this case x equals 4, you can see that we get an even amount of area on the left and the right. So let's go ahead and look at some examples of modeling with the normal distribution. Example 1, pressure gauges manufactured by Precision Core must be checked for accuracy before being placed on the market. To test a pressure gauge, a worker uses it to measure the pressure of a sample of compressed air known to be at a pressure of exactly 50 pounds per square inch. If the gauge reading is off by more than 1%, it is rejected. Assuming that the reading of a pressure gauge under these circumstances is a normal random variable with mean 50 and standard deviation 0.4, find the percentage of gauges rejected. Okay, so what we have is a distribution of pressure gauge reading. So x equals the PSI measured. And we know that this distribution, and normally here we don't draw a vertical axis because this normal distribution does go on forever, but at mu equals 50, we have our distribution. We'll just go ahead and sketch something here. There's mu equals 50, and sigma, the amount of spread, sigma is going to equal 0.4. Now, we know that if the gauge reading is off by more than 1%, in other words, if this is 50, we only are in a safe tolerance if we're within half a pound of the 50 psi. So we want to be between 49.5 and 50.5. So these are the ones that will be accepted, but we want this area here. We want the percentage of pressure gauges that will be rejected. So there's two ways we could do this. One is to find the area to the left of 49.5, find the area to the right of 50.5 given a distribution with mean 50 and sigma equals 0.4, and then subtract that from 100% to give us this amount here. Another way I could do this is if I want the purple area, I can just take 1 minus the probability that x is between 49.5 and 50.5. Now, one thing to note is that the less than or equal to is not of importance, because we know that the probability of an exact value occurring within a continuous distribution, that probability is 0, because there are infinitely many values and the probability of getting exactly one specific value is 1 out of infinitely many, which is 0. So I'm going to find it like this. I'm going to take this entire area, which is 100%, subtract away what I don't want. That will just allow me to do one computation instead of two separate ones. Let's go over to our probability simulator. And let's go ahead and change to the normal distribution. In our case, the mean is going to equal 50 with a standard deviation of 0.4. Okay, so we can see that there's going to be a very tight window between 49.5 and 50.5 where we're going to accept those pressure gauges. And so one way that we can do this is we can do this one of two ways. We want to find the area between, let's see here. Okay, there we go. So now we can change this to 49.5 and 50.5. So that means 78.87% of our pressure gauges are going to be within the desired tolerance, but 1 minus that, or 0.2113, which is 21.13%, will be rejected. Now it looks like we can also just find the probability if we select this option here, then there we go. We can actually do 49.5, find that area, and also find 50.5, just 0.2113. Gives us exactly the same answer. So there's just under a quarter of the pressure gauges will be rejected. They're not going to be within the required tolerance. Let's take a look at one more example. The values of mortgage loans made by a certain bank 1 year were normally distributed with a mean of $120,000, so $120,000 mortgage loans, with a standard deviation sigma equals 40,000. So already I'm just going to go ahead and just do a quick sketch of this. This is going to be mu equals 120,000 and sigma equals 40,000. What is the probability that a randomly selected mortgage loan was in the range 40,000 to 200,000? Okay, so 40,000, say, is here. 200,000. So it looks like 80,000 to the left and to the right. And I want to know what is this area right here. So I'm going to go back to my probability calculator, change this to 120,000, change sigma to 40,000, and now I'm going to select the internal range here to go from, we want this to be from 40,000 to 200,000. Change this to 40,000, change this one to 200,000, and I see that about 95.45%, and let's write this probability statement out. This is probability that X is between 40,000 and 200,000, which is 0.9545, which is 95.45% of all loans were between $40,000 and $200,000. Now, in letter B, you would like to state in your annual report that 50% of all mortgage loans were in a certain range with the mean in the center. What is that range? Okay, so we want to describe effectively the middle 50%. So here once again is that distribution, and we have our mu equals 120,000, sigma equals 40,000. And what we know is that we want to locate the middle 50% such that the mean is right in the center. I want this area to be 50% of the overall area. So what I'm looking for here is I'm looking for an x min and an x max such that 50% is contained in between those two values. Okay, so how would I go about doing this? Well, one primitive way is to, first of all, take a look at this and make our values equally spaced so that I change this to be, well, first of all, it would have to be closer to the mean. So maybe we'll go 100,000. So that's 20,000 units below the mean, and then I need to go 20,000 units above the mean to 140,000. Okay, so there the area is too small, so 0.3829 is not quite there. So let's go up to 110,000, or I'm sorry, 99,000, and let's bump this up to 100. Let's see, we went down 1,000, so let's go up 1,000 here. So we're getting closer. That's 40%. Now we can go to, say, 98 and 142. That gives us 41.77%. We can go 97 to 143. We're getting closer. It might make sense to maybe, now that we're 3,000 to the left and to the right, maybe we're going to go down to 95,000 and make this up to 145,000. So we're getting closer. Let's make this 92,000 and make this 148. Again, that's equally spaced. That's a little too big, so maybe let's go 147,000 and 93,000. And there we go. We're pretty close. That's about 50%. Now we'd have to change, the hundreds of dollars instead of the thousands of dollars, and that's really not going to really describe home values much more precisely than saying 93,000 to 147,000. So x min, we'll just say, is approximately 93,000, and x max is approximately 147,000. And that means that we could also write it like this. We could say that the probability that that a loan is between $93,000 and $147,000 is about 0.5. It's about 50%. And there are other ways of doing this, but at this point it simply is a little bit easier to kind of do this guess and check. Now here's one other option. If this is centered about the mean, then that means that this region is going to be 25% and this region is going to be 25% because of the symmetry of the normal distribution. So one way to make this a little bit easier is to just change this to be from the mean, which is 120,000, and go up to, say, 150,000, and then try to get this close to 25%. Then take the distance between the mean and the value, and that's going to be the same distance on the other side of the mean. So let's see, this was 140, that's too small, 145,000, 146,000, 147,000. So 147,000, that's a difference of 27,000. And so now I could say 120,000 minus 27,000, which would be on this other side, would be 93,000, which would give me that x min value as well.